let's talk about artificial intelligence. You hear this term thrown around all the time, right? The black box. It's this idea that we have these incredible machines that can give us amazing answers, but we have absolutely no clue how they do it. It's kind of spooky when you think about it. But what if we've been looking at this whole thing the wrong way? Let's crack this thing open.
So, is that it? Is this our future? Just trusting these incredibly powerful AIs without ever really getting what's going on inside? A lot of experts would say, yeah, that's just the price of admission. This opacity is just part of the deal. But a really fascinating new study is suggesting there might be another path forward.
What if we could actually build a window into the AI's mind, see what it's thinking? Well, that's exactly what this study tried to do. The goal was to prove that unknowable doesn't have to be the final word when it comes to AI. Okay, so let's get into what we call the opacity problem. Why do we even care if AI is a black box? Well, this isn't just some academic puzzle for computer scientists. This has huge real-world stakes. I'm talking about our health, our safety on the road, you name it. Just think about it for a second. An AI is controlling a self-driving car. If it makes a mistake, we have to know why, so we can make sure it never, ever happens again. Right now, if an AI that's diagnosing diseases gets something wrong, often the only fix is to scrap the whole thing and retrain it from scratch. That's not just a waste of time and money, it's a massive roadblock. We're essentially flying blind, trying to build better AI without understanding how the current ones even work.
For a long time, the dominant idea has been, look, these systems are just too big, too complex for our little human brains to ever really wrap our heads around. This quote on the slides says it all, that the opacity is just a baked-in feature, maybe even unavoidable. It's like trying to map every single neuron in a human brain. Just seems impossible, right? But what if there's a way to test if that's actually true?
And that is exactly where this study comes in. The researchers decided to try something totally different. Instead of wrestling with a giant, complex AI, they basically put a really small one under a powerful microscope. The goal? To map out every single process, every single thought it had. Now, I know what you might be thinking. Handwritten digits? That's ancient. And yeah, you're right. But that's the genius of this experiment. Using a simple AI on a classic, well-understood task wasn't a limitation. It was a brilliant scientific control. It meant they could see everything. No hidden corners, no confusing complexity. They traded raw power for absolute crystal clarity. And just to put the scale here in perspective, the AI in this study had just under 13,000 parameters. A modern vision AI, well, that's got over 25 million. And a large language model like GPT-3, a mind-boggling 175 billion. So yeah, the difference is staggering, and it really shows you how focused and deliberate this experiment was. So how did they do it? Their approach was incredibly methodical. They created a 4-step process to examine the AI's brain from every possible angle. You can think of it like a complete medical checkup for the AI. They looked at its overall structure, they examined its individual cells, they watched how it processed information, and then, this is the cool part, they tested what they learned with a hands-on experiment.
Okay, so what did they actually find when they peeked under the hood? This is where it starts to get really, really cool. Instead of finding a chaotic mess of connections, they started seeing clear evidence of a well-organized, structured system. So the very first thing they noticed was about geometry. See, the raw data of handwritten numbers is messy, right? A 1 can look a lot like a 7. A 3 can look like an 8. The researchers saw that the AI's first job was to be a super organizer. It took all that messy data, and internally it rearranged it, almost like tidying a room. And the result? It made the different digits a full 3 times more distinct and easier to tell apart. But how does it do that organizing? Well, it uses its artificial neurons. And a key question was, is each neuron a jack of all trades, doing a little bit of everything? Or is it a specialist? A specialist neuron has a fancy name, monosemantic. It's like a worker on an assembly line who has one and only one specific job to do. And what they found was absolutely stunning. A whopping 87.5% of the neurons in this AI's brain were specialists. Each one had taught itself one very specific job, like look for a straight vertical line, which is useful for the number 1, or look for a closed loop at the bottom for the number 8. This isn't chaos at all. This is a highly organized workforce. And it gets even better. These specialist neurons weren't just working by themselves. They were forming small, super efficient teams. To identify any given number, the AI would use a specific, dedicated circuit of just a handful of neurons. So, like you can see here, recognizing a 7 was the job of a very specific 3-neuron team. This isn't some tangled, unknowable web. It's a collection of clean, understandable mini-programs.
So all the evidence points to this AI being neat and organized. But, seeing is one thing, proving it is another. To truly show they understood how this thing worked, the researchers decided to do the ultimate test. They were going to perform brain surgery on the AI. The first thing they did was break it on purpose. They fed it bad data. And they taught it that every single 7 it saw was actually a 1. And, no surprise, its accuracy for recognizing the number 7 dropped straight to 0. The mission, then, was to go in with a surgical scalpel, find the one broken part, and fix it, all without having to retrain the entire system. The technique they used is called ROME, which stands for Rank 1 Model Editing, and you should really just think of it as microsurgery for an AI. Instead of some big, messy operation, they used that detailed map of the AI's brain they'd made to find the exact single faulty memory. Then, they calculated the absolute tiniest change needed to correct it and applied the fix, leaving everything else completely untouched. So this is where they started. A complete failure. The AI gets the number 7 wrong 100% of the time. And here's the result right after the surgery, an absolutely incredible recovery. Its accuracy on the number 7 went from 0 to almost 98%. They actually did it. They fixed it. But this is the most amazing part. To get that nearly perfect fix, they only had to change 0.28% of the AI's connections. That's it. This wasn't a sledgehammer approach. It was a scalpel. And it's pretty much definitive proof that they understood the mechanics of this system with incredible precision. So after all that, what does this mean for the big picture? Have we finally solved the black box problem once and for all? Well, the verdict from this study is loud and clear. For an AI of this size, on this task, the black box myth is completely busted. The inside of this machine wasn't a mystery at all. It was a clean, structured, and even surgically repairable system. It shows that this kind of deep understanding, what they call mechanistic transparency, is actually possible. But, and this is the billion-parameter question, isn't it? Does this scale up? The AI in this study was like a rowboat. The AIs that power our world today are more like aircraft carriers. The leap in size, complexity, and even the basic architecture is just massive. And it's not at all clear if these same transparency techniques will work on that kind of gigantic scale. So where does that leave us? Honestly, this study is a huge beacon of hope. It's proof of concept. It tells us that AI doesn't have to be a mysterious black box. We've now seen a glimpse of what a fully transparent AI looks like. The next great challenge for the entire field is figuring out if we can turn that tiny glimpse into a panoramic view. And finally, truly understand the minds of the machines that we're building.